Welcome to another tutor short provided by the Educational Support Services Department of Lehigh Carbon Community College in Schnecksville, Pennsylvania, which is just outside of Allentown. These videos review key learnings for the science courses provided here at L-Tri-C. And please remember that the Educational Support Services Department does provide walk-in tutoring 5 days a week. In this video, we're going to review under nuclear chemistry, radioactive decay. Here I'm showing here the overall a summary of nuclear chemistry. I start out with mentioning that chemical reactions are when you have interactions with the valence electrons of elements. So you're having reactions between elements where the electron clouds are having interactions. The nucleus of your atoms are not involved in the reactions or not really affected. However, in the nuclear reactions, now you're not dealing with the electron clouds around the nucleus. You're dealing with the nucleus itself and changes and interactions with the nucleus of the elements involved. So there are three types of nuclear reactions: radioactive decay, fission, and fusion. Fission and fusion we're going to do in another video. In this video, we're talking about radioactive decay, which is when a nucleus spontaneously breaks down by emitting some form of radiation. So you have a unstable nucleus that is breaking down to form a more stable nucleus. Fission, just to finish this out, fission is when nucleus will split into two smaller nuclei, and if that then results in further on in causing more reactions, then we'll call that a chain reaction. And again, and when we do the video on fission and fusion, we'll talk about the chain reactions. And then fusion, again, is when two small nuclei come together to form a larger nucleus. So those are the types of nuclear reactions. Today we're dealing with radioactive decay. And when we talk nuclear reactions, we need to talk about a bunch of the nuclear particles that are involved. And so a alpha radiation, it's represented by this Greek symbol here, this one here. And an alpha decay is when the nucleus loses 2 protons and 2 neutrons. And that's essentially a helium nucleus. No electrons around it, just the nucleus itself from a helium atom. The charge is +2 and the mass is 4. And the symbol we'll use in our when we show nuclear reactions, we'll show helium, the helium nucleus, with 4 is the atomic mass number and 2 is the atomic number. And I sometimes like to put a 0 over here, which is where you represent the electrons. Put a 0 there so there's no electrons involved in this. It's just 2 protons and 2 neutrons. In beta decay, your beta radiation is represented by this symbol here. Beta decay is the release of an electron from a nucleus. An electron has a -1 charge. The mass is negligible. It's only it's like a thousandth of an AMU, so you can ignore the mass change. And we represent that. It's an electron, so we use an E. It has 0 mass, but it does have a -1 charge. Is the way we show it. A positron decay, we show that as this symbol of a B here with a plus charge on it. That's what's being released from the nucleus is an antimatter electron, which is essentially an electron that has a positive charge instead of a negative charge. So we show the +1 charge. Again, the mass is negligible. And now we're going to show E again, only we're going to show a 1 for the plus and the 0 for the mass number. In gamma radiation, we have this symbol here. And a gamma radiation isn't really a particle. It's a photon of electromagnetic energy. Essentially, it's just energy being released from the nucleus. So there is no change in charge in the nucleus, no change in mass of the nucleus. And we represent that again with this gamma representation of a symbol with 2 zeros. There's no mass change and no charge change or proton change. And then you'll see as, again, back to our normal particles that we're used to, proton is normally represented as a P with a plus, and a neutron, an N with a 0. You should be familiar with those already, but they are involved in the nuclear reactions. The charge of the proton +1 with a mass of 1, and a neutron, no charge but a mass of 1. And so typically a proton, is going to be shown. I always use a P, but in this case we want to use that it's essentially a hydrogen nucleus with just one proton and no neutrons. So we represent it as an H, a hydrogen nucleus. And neutron, again, you just use the N for the neutron, a 1 and a 0. It has a mass number of 1, but there's no charge with it. So in your nuclear reactions, it's the way they normally show the symbols for these decays is they use the symbol on here on the far right column for the symbols. So now let's review the 4 different types of decays under nuclear reactions here. In an alpha decay, we're going to use americium here. We're starting with this radioactive compound. Americium, an unstable nucleus, it has a 241 mass number and a 95 atomic number. And in an alpha decay, it's going to lose this. It's going to use an alpha particle, which is a helium nucleus with 2 protons and 2 neutrons. So the simple way you would work out what happens in a reactive decay here is you're starting with your americium and you're going to remove 2 protons and 2 neutrons. So if we start with the protons, the 95, what we're going to result here is there's going to be 93 protons because 2 of them go off with the alpha decay, and the mass number is going to go down by 4. So you're going to have 237 is going to be your mass number. And if you look at the 93 here, the proton count, what tells you what element you have, this is going to be neptunium. So in an alpha decay of americium, you're going to get neptunium or neptunium, however you pronounce it, and release a alpha particle from that reaction. Now when we go to a beta decay, in this case we're emitting an electron from the nucleus. What happens here is a neutron in the nucleus breaks up into a proton and an electron. So that a neutron is going to degrade inside the nucleus of that atom, and the proton is going to remain in the nucleus, but it's going to emit from the nucleus an electron. So when we look here at carbon-14, a very common radioactive material you heard about in carbon-14 dating, what's going to happen is now the 6 here, number of protons, it's going to go up because we've added a proton. So now you're going to have 7 protons. The mass number, though 14, is going to stay the same. All you did is change a neutron to a proton. Overall, the sum is going to stay at 14, and your electron's going to go off. Now that your mass atomic number is 7, we now have nitrogen. So the new element formed is nitrogen, and an electron is released from the nucleus. In a positron decay, now a proton in the nucleus is going to break up into a neutron and a positive electron, or an anti-electron, antimatter, and that's called a positron. So it's essentially an electron with a positive charge. So a positron is emitted from the nucleus, and now a proton in the nucleus is changed to a neutron. So in this case with aluminum, our 13, I'll use green here for you, our 13 on our number of protons is going to drop down to 12. So one of those protons was converted to a neutron. Your mass number is going to stay the same, 24. The positron is going to fly out of the nucleus. And what's left, your mass, your atomic number of 12, tells you now that you have magnesium. So you have formed magnesium, and a positron has been emitted from the nucleus. In the last decay, we're going to use represent a gamma decay here. A gamma decay is strictly a decay in energy. So you have an unstable nucleus here, unstable nucleus. It's going to release some energy in the form of a gamma ray. A gamma ray is represented by this, but because there's no release of a particle, no electron or neutron or positron, any kind of particle come out, it's just energy, you still have your mass number of 99, and you still have your proton sum of 43. So you still have technetium, Tc. You still so your element has not changed here. All you've done is lost energy, and now you have formed a stable nucleus. So gamma radiation is just a release of energy, and there's no particles involved. Now, last thing we want to talk about is how are radioactive isotopes formed. Generally, you won't have too much in introductory courses, too many homework assignments or whatever involved with radioactive isotopes, but it's normally presented in the chapter, and so we're going to go over it here. You can form a radioactive isotope by bombarding a stable nuclei with a high-speed particle. And as a result, the stable nucleus is converted into a radioactive nucleus, if you want, or isotope. So the two examples I show here, in the first one, we're going to take nickel, and we're going to bombard it here with a hydrogen nucleus, 1 and 1, which is a proton, plus 1 charge, and no neutrons involved. So a hydrogen nucleus here, essentially just a proton, is bombards a nickel compound, and what's going to be emitted is an alpha particle. Basically, as far as I'll say homework's involved, they'll tell you what's going to be emitted, an alpha particle, and they'll then ask you what is formed if an alpha particle is released in a reaction like this. And again, you would just do a mass kind of balance. You would look over here and say, well, I have a total of 59 total mass number, and I know 4 is coming off here in the alpha decay, so therefore that leaves me with 55 over here. You would do your summation here. You started with 29 protons, you lose 2 over here, therefore this must be 27, and once you know you have 27 here, then you know that what is formed is cobalt. So again, most of the problems, when you get a homework problem, you'll be just playing with your mass numbers and your atomic numbers and matching everything up. So this would be the result of a proton impacting a nickel. Another example here is we're taking just nitrogen and hitting, bombarding CF, and I can't remember offhand what CF is. Oh, californium, that's right. Sorry about that. Californium is being hidden with nitrogen nucleus. In this case, you're going to release 4 neutrons. So you have 4 neutrons coming off, So when you look at your mass balance again to see what this material is going to be over here, you have a total of 264 total mass number on the left, and you have 4 neutrons coming off. So if this is 264 and there's 4 coming off over here, that leaves you with 260. On the proton sum here, you've got 98 and 7, gives you 105. And as you know, a neutron has no protons in it, so all of the protons end up with this element here. And so now that you've done your mass balance, the 260 and the 105, then you know you have dubnium dB here is your resultant nucleus or element that you're forming. So again, in some of these you'll see you'll get multiple emitted particles coming out of it when you form some radioactive isotopes. But I wanted to represent basically it's a matter of balancing out your atomic mass, your atomic numbers, your protons and neutrons, and just balancing them out in order to do these problems. Thank you.